Hi everyone, we're going to talk about EDTA titrations in this video, and our goal will be to calculate that free metal ion concentration at any point in the titration. Sometimes you're asked to find the Pmn plus, which is just the negative log of that ion concentration. P means negative log. You can take the negative log of anything. So don't be alarmed if you're ever asked to find the negative log of the metal ion concentration. That's all P means. So let's try an example. Here is our titration. We've got some EDTA in our burette, and in our Erlenmeyer, we've got 25 mils of this concentration of calcium. They gave us the pH, and that was nice of them to also give us alpha at that pH and the log of the formation constant for calcium. Now, to get the initial PCA, it's no big deal, but I just want to be prepared for what comes next. So I'm going to write down the titration reaction, which will be calcium reacting with EDTA to form that calcium EDTA complex. Maybe while we're at it, why don't we get the conditional formation constant, which will be alpha times Kf. Well, they gave you the log of Kf, so take the anti-log of that number, and you'll get 4.47 times 10 to the 10th for a conditional formation constant of 1.3 with an insignificant 4 times 10 to the 10th. Pretty big. The other thing that I might want to do, just so I don't get confused, would be to calculate the equivalence volume. And just as for acids and bases, in those titrations, there was more than one way to get an equivalence volume. The same is true here. Do it the way that makes sense for you. Since you have a one-to-one stoichiometry, you can call this C1 and this V1, and you can call this C2 and solve for V2 if you wanted, or the way that I would do it is I would use solution stoichiometry. I know this is my calcium ion concentration in moles per liter. I know the volume, which I can convert to liters. And I know that for every 1 mole of calcium, I'm going to use 1 mole of EDTA. And my EDTA concentration is given right here. And then one final step to get from liters into milliliters. And when you do that, you should get an equivalence volume of 20.0 milliliters. So either way, either you use C1V1 or you use this solution stoichiometry, that's the equivalence volume. Again, you really didn't have to do this to get the initial PCA, but I just want to be ready for the rest of the problem. So finally, PCA would just be the negative log of that calcium ion concentration, and I got 3.699. And just a gentle review, 3 sig figs in N, so we need 3 digits in the mantissa of A. Let's keep going. And now they want us to calculate PCA after 8 mils of this EDTA have been added. So clearly we are before the equivalence point. So what's true at this point in the titration? At this point in the titration, every time you add EDTA, it gets consumed. So at this point in the titration, your solution will contain excess calcium and this complex. Now, do you think you're going to have to worry about the little bit of calcium produced from dissociation of this complex? Probably not. We just need to figure out how many excess moles of calcium we have at this point in the titration. So you know how I'm going to do it. I'm going to make an ice table. So here's my reaction. And what do we have initially? Well, I know the concentration of calcium, I know the volume. That gives 5.00 times 10 to the negative fifth moles of calcium initially. And similarly for EDTA, you know the concentration, you know the volume that was added. That gives 2.00 times 10 to the negative fifth moles. And initially you haven't even made any complex yet. So now look at our limiting reactant. We'll be subtracting those moles from the reactants and adding them to the products so that at equilibrium we have 3.00 times 10 to the negative fifth moles for calcium. EDTA got consumed, and we have made some of this calcium EDTA complex. And yes, a little bit of this complex can dissociate to produce some free calcium, but it's going to be so small compared to the free calcium that you have here, right? We have free calcium ions here. We've got bound calcium ions here. And what do I mean by bound? Bound by EDTA. So we're going to ignore the calcium from this complex. So then to get the calcium ion concentration, it's just these excess moles divided by the total volume. Well, you started off with 25, you added 8, I think that's 33. And that gives a calcium concentration of 9.09 with an insignificant 1 times 10 to the negative fourth molar. And taking the negative log of this number gives you pCa, and I got 3.041. So that was before the equivalence volume. I think you know what volume is going to be next. Yes, at the equivalence volume. So what is true about this solution at the equivalence volume? You've added enough EDTA to bind all of the calcium. So EDTA is gone, calcium is gone. All you have in this solution is the complex. And didn't we already do a problem where we had to calculate the free metal ion concentration in a metal EDTA complex? Yes. Who cares if this complex was formed by titration? We did it before, so we can do it again. All we need to do is figure out the concentration of this complex, so I'm going to rely on an ice table to do that. My initial moles of calcium haven't changed. It's still 5.00 times 10 to the negative fifth moles, and the moles of EDTA are also the same. And you can prove that to yourself. You've got concentration, you got volume, you should get this number. So now we'll subtract these moles from the reactants, add them to the products. So that at equilibrium, calcium is gone, EDTA is gone, and we've made some of that complex. And I kind of like to think of this as a pseudo-equilibrium, because a little bit of this complex dissociates to form free EDTA and free calcium, such that at our real equilibrium, we have X for calcium, X for EDTA, and 5.00 times 10 to the negative fifth moles minus X for the complex. But again, X is going to be small because this equilibrium lies so far to the right, we always ignore it. So now we can plug and chug into our K primed F. That'll be products. Well, we probably should get this concentration of the complex. Let me set up my K primed of F first. Products over reactants. X is calcium, so I might just call that calcium squared. And now I'm going to rearrange for calcium. It looks like that's going to be the square root of the complex over the conditional formation constant. And maybe now would be a good time to get the concentration of that complex. Maybe we can do it right here. It's 5.00 times 10 to the negative fifth moles of that complex over the total volume. You had 25, you added 20, that's 45, or 0.0450 liters. And that gives a concentration of 1.11 with an insignificant 1 times 10 to the negative third molar, dividing by K primed of F, and taking the square root gives 2.8 with an insignificant 8 times 10 to the negative seventh molar, and that is calcium. Look how small that is. And taking the negative log would give you 6.54. So at this place in the titration, it's just like that problem we did earlier. How did we find the free metal ion concentration in a metal EDTA complex? Well, we've got one place left, and that is beyond the equivalence volume. In this case, after adding 30 mils of EDTA. So what is true beyond the equivalence volume? Not only have you added enough EDTA to bind all of the calcium, you've added excess EDTA. So at this point in the titration, this solution will contain the complex and excess EDTA. We better figure out those concentrations using an ice table. My initial moles of calcium aren't going to change. We calculated those a while ago. And now for the initial moles of EDTA, you know the concentration, you know the volume that was added. That works out to be 7.50 times 10 to the negative fifth. And the moles of complex initially are 0. So now, looking at your ice table, you see that calcium is the limiting reactant. So we'll subtract that from the reactants. And add that to the products. So calcium is 0. We thought it was going to get consumed. We have some excess EDTA. And we've made some of the calcium EDTA complex. And again, this is what I think of as the pseudo-equilibrium. What happens next is a little bit of this complex dissociates to produce a little bit of free EDTA and a little bit of calcium. So at our real equilibrium, we have X for calcium, 2.50 times 10 to the negative fifth moles plus X for EDTA, and 5.00 times 10 to the negative fifth moles minus x for the complex. X is going to be small, so you can ignore it. And now we can use our conditional formation constant. K primed of F is going to be products. That's the complex over reactants, so it'll be calcium and EDTA downstairs. And solving for calcium gives, let's see, I think that's going to be the complex upstairs, the conditional formation constant downstairs, and that formal EDTA concentration downstairs. And we really do need to get the concentrations of the complex and EDTA, but I want to show you something. The concentration of the complex would be 5.00 times 10 to the negative fifth moles of that complex over the total volume. You started off with 25, you added 30, I think that's 55 or this many liters. And then we're going to be dividing by K primed of F. And again, we need the concentration of this EDTA. It'll be this many moles. Over the total volume. Well, that total volume is the same. And that's why I chose to do the problem this way, just so you could see that volumes cancel. And at this point, we could have just used moles in our calculation, but it's always nice to prove that to yourself. So when I did the arithmetic, I got 1.4 with an insignificant 9 times 10 to the negative 10th molar. Look how small that is. And if you take the negative log, that'll give you PCA, and I got 9.83. The last thing we have to do is to sketch the titration curve, but maybe we'll save that for a different video. I hope you try some of these calculations on your own, and thanks for listening.